There you go. So let's start. First, well, I'm going to draw something here. We are going to start working. Well, we always have people, so our goal is to provide people with comfort. And what are we going to do? Then we're going to design the envelope, and then we're going to calculate the thermal properties of that envelope. Okay, so this is the people, and finally, at least we'll have a roof. And the most important element in the building envelope for us is the thermal insulation. So we assume that we have a very thick thermal insulation. We always have this hatch for the thermal insulation, and then after the roof, we will have walls and windows. So let's create the wall. Okay, so remember that we do have thermal insulations, and this is something that we have to learn how to create a continuous thermal insulation. And then we have windows. Windows are transparent elements. We need them because we need natural light, we need natural ventilation. But when it comes to thermal insulation, windows are the weakest point of the thermal envelope. We have to be careful without that. And then there are, yeah, we have the walls, and finally, this is the floor. There you go. Okay, as I told you, we have transparent and we have non-transparent elements. So this is the outdoors, and we have an incredible source of energy, which is the sun. Okay, so we have sun, and sun provides us with heat. Okay, so if we are in winter, we can make the most of the heat of the solar radiation. We can keep 70 Fahrenheit inside. If it's a cold day, a winter day with 20 Fahrenheit, there will be a lot of heat going out through the envelope, through the roof, walls, floor, and window. This is very important. We can, those are heat losses. So there will be a lot of heat losses in this envelope, because if we have 70 Fahrenheit here, 20 Fahrenheit there, so there will be, the heat will move from the hot or the warm temperature to the cold temperature. This is what heat does. But we have the source of heat even in winter. If we have a sunny winter day, there will be a lot of solar radiation entering the building through windows. So that's why, if this is a south-oriented window, because the sun in winter, it's mostly, it's in the south, it rises in the east, it sets in the west. This is not true, by the way, but most of hours, most of daytime, we have the sun in the south, or heating the south facade. So if we design good windows with the right orientation, we can make the most of this solar energy. On the other hand, if we have windows in this north elevation, there will be a lot of heat losses. Okay, so designing windows properly, it can save a lot of energy. But this is the basic problem. We have 70 Fahrenheit, which is comfort temperature inside. 20 Fahrenheit, it's winter. We have people living in our building, and basically we are losing heat if we are talking about winter. But at the same time, through windows, especially through the southern window, we are gaining heat. So at the end, the balance, it's the heat that we lose and the heat that we gain. If this balance is zero, we have a zero energy building, which is the goal of that course. We have to start designing zero energy buildings. A zero energy building, it's a building that doesn't consume any energy. Or, no, that's not correct. It's a building that consumes the same energy that it generates. Okay, so we can have active energy generators in our building, like solar collectors or photovoltaic panels. So at the end, if the balance between the heat losses, the heat gains, and the energy we are producing is zero, then we have a zero energy building. So this is our goal. by 2050, all buildings on Earth, well, on Earth, all buildings, at least in the United States, in Europe, it should be zero energy building. By 2050, 2050 is almost there. So I'll be dead, most likely, but you will be architects, and yeah, you will be at the top of your professional activity by 2050. So you have to start learning today something that you will apply in 2050. It doesn't mean that today you can't build or you can't design zero energy buildings. Of course you can, and it will be demanded, and you will have a lot of clients if you are able to do that. But by 2050, it will be mandatory, at least in Europe, the United States, and most of countries on Earth. Okay, so make sure that you understand this from the beginning, and this is what we are doing in this course, to introduce you to this zero energy building principle. Okay, so this is a way to show the same. So we have warm temperature inside, cold temperature outside. We are losing a lot of energy through the walls, through the roof, and we are gaining energy through the windows because of the solar radiation. If the balance is not zero, I mean, if we are losing more energy that we are gaining through the sun, we need a heater. We need a heating device. If we are not generating a zero energy building, we need to dimension this heater. So we need to let our client know what the power of this heater is. Okay, so what device he has to purchase in order to provide this house with this temperature. Okay, because this is our goal. It's not, we can save energy, but reducing this temperature, but our clients won't be in a comfortable condition, so we cannot do that. Okay, so we need comfort for our clients or for the building users, and we need the minimum energy consumed by this heater or the heating device. I have taken this from that book, from the Builder's Guide, Cold Climate. So we're not going to study details yet, but I think it's good for you to start understanding what a high performance building or what a zero energy building is. The goal is a zero energy building. As we are getting to this goal, or as we are arriving at the zero energy building, we have different stages. We have the high performance building. If you have been to the TDS center, if you know that building, this is a high performance building. It's not a zero energy building, but it's a building that it's quite good. It was built like, I think it was 5 or 6 years ago in 2014. It's a high performance building. It's much better than other buildings in campus, and not only other buildings in campus, but it's in the above the level when it comes to buildings in the United States and Europe, because it has high thermal insulation, it has a very good window design, it has a PV array. So if you look at the roof, there is something on the roof, which is the PV array, the photovoltaic array. So it's producing a lot of energy. It doesn't produce as much energy as it consumes. That's why it's not a zero energy building, but it's a building that is above the average. So that's why it's a high performance building. Then we have the nearly zero energy building. A nearly zero energy building, it's not a zero energy building, but it's almost there. And then by 2050, all buildings should be zero energy buildings. Okay, so on our road to the zero energy buildings, at least we can start with a high performance building. So what is a high performance building? It's a building that first has efficient windows. We are talking about cold and very cold climates. So what are the design features? What do we have to do? First, we have to design efficient windows. We will devote a lesson only to the windows because it's not something that we can design. We have to select the window because windows are manufactured in glass plants, so they manufacture the window that we need, but we need to specify the correct features of that window. So we can't design, but we can specify what kind of window we want. Second, we need compact and tightly sealed duct runs. So this is the key word here is tight. So we need to design tight windows. You see that we have duct runs. So those are ducts. Okay, so especially single family houses, we do have ducts, but it's not that common. But in public buildings or in commercial buildings, we need a mechanical ventilation and there are ducts. So those ducts are going through walls, sometimes are going through the roof. So we need to seal tightly those duct runs. Okay, so if we have this duct going through that window, we have to seal this because otherwise there will be air leaks, and air leaks means that we are losing a lot of energy. Third, we have to right size the HVAC. HVAC stands for heating, ventilation, air conditioning equipment. Okay, so this is the heating, the cooling, and the ventilation system. So we have to design this, and we will learn how to do that in building systems next year. Third, no, this is the fourth. We need ventilation. We need ventilation because as we breathe, as we inspire and expire, we are releasing a lot of, what we are releasing nowadays, a lot of things. But one of the things we are releasing is water. Okay, so we need to get rid of this excess of water or these viruses or whatever. We need to ventilate buildings now more than ever. And ventilation has become something important because by using a room, we breathe, we move, we sweat. So there are a lot of things that we have to get rid of. Okay, so ventilation now it's becoming more and more important to prevent diseases from spreading the building. Sealed combustion appliances. Okay, so here we can have boilers, furnaces, chimneys, or fireplaces. Again, we need to seal all these things. The same thing we did with the air ducts. We need to make sure that we don't have air leaks in these kind of places. Those are, well, let's continue. I don't comment this so far because I want to go over the insulation. So we need to design the right thickness for this insulation. Okay, so this is the thermal insulation, this material we have here. And we need to design the correct thickness. And we need to reduce we need to increase the thermal resistance, and then we need to reduce the thermal transmittance. So the rest of the layers that we have in our wall, when it comes to thermal resistance, well, they don't make any difference. The material that makes a real difference is the thermal insulation. So that's why having thick thermal insulation layers provides us with the right thermal insulation for our building. So don't be shy. If this has to be at least, I think we said 6 inches at least last week. It can be more. It can be 10, it can be 12, it can be 20. Why not? It depends on how big our building is. But if we are going to, if our goal is to design a zero energy building, you have to get used to designing thermal insulation more than 10 inches at least. In cold countries, if we are in Florida, maybe 6 inches is enough. But if we are in New Hampshire, 10, 12 inches, it's something that it's not unusual. We need air sealing. Not only do we need air sealing in ducts or in fireplaces or whatever, we need air sealing when we have corners, the connection between the roof and the wall. This is very important because we have to prevent leaks from happening. You see that here in the connection between the floor slab, this one, and the wall, we have this element, which is the air sealing. There might be a crack, and then the hot air can go, or the warm air can go out through this crack. So we need to seal, especially connections between walls, corners are weaknesses, the connections between slabs, roofs, and walls. Okay, so we need to seal all these elements. Moisture barriers and drainage pathways. That's very important, but we are not going to talk about this year. Well, this course, because this is something that we cover in Arch 360, which is solar design. It's a course in the second semester. It's an elective, but we don't have enough time to talk about moisture barriers and drainage in this course. Okay, but it's important, and it has to do with the air sealing, because both issues are connected. If we don't have a good air sealing, there will be moisture issues as well. Well, all these things are the things that we have commented so far are good, especially for winter. The overhangs or eaves are things that we have to design in summer, because we have two issues. In winter, the warm air, we have the warm air here indoors, and it tends to go out. But in summer, it's the other way around. So in winter, it's great. If we have huge windows, especially facing south, we can make the most of them, as we see here. Okay, so we can see that those windows, if they are well oriented, we can have a lot of heat gain through the window. So in winter is perfect. But what happens in summer? In summer, we don't need this. Okay, so by designing overhangs and eaves, we can cast shade on our windows in summer. This is what we need. And this is design, this is architectural design. We don't depend on mechanical engineer. We have to design the right windows in winter. So we need to expose those windows to the sunlight in winter, but in summer, we have to cast shadow on that window. And that's a question about geometry. This is about geometry. We need to know the sun path on the sky, and it's very easy to know that. And then we need to control the height of the window and the length of overhangs or eaves. What is an overhang? Okay, those are overhangs. You see that we have a window here from floor to the ceiling, and we extend the roof so that in summer this roof is providing, or so it's casting shadows on this glass. So this is basic. When we are talking about zero energy buildings, when we are talking about bioclimatic architecture, designing good overhangs, it's very important. Okay, I think I told you that the master of this concept, it's Frank Lloyd Wright. So Frank Lloyd Wright, when he was 80 years old, he died when he was 90 or something like that. But when he was 80, he decided that he wanted to apply all his knowledge of a lifetime learning about architecture to single-family houses, to humble single-family houses. And he invented this concept of Usonian houses by Frank Lloyd Wright. And he designed, I don't know, maybe hundreds of them. Okay, and if you can see all these single-family houses, they have the same concept. They have large windows facing south, and they have these overhangs here. But if you look at the north elevation of this single-family, no, it's not what I wanted. Okay, if you look at the north elevation, it's completely different. The north elevation has very small openings like this, and it doesn't have overhangs because we don't need overhangs in north elevation. Okay, but this is the contrast. So that works well. So especially if you are designing small buildings, having the north facade like this, very massive with small windows, and having the south facade like this with huge windows and long overhangs, that's a key to success. Okay, so if at the end of this course you learn that the south elevation is different from the north elevation, in the south elevation, if we are working in New Hampshire, or if we are working in a cold country, if we are working in Florida, probably this is not the right option. But if we are working in cold climates, this is a key to success. So we have to design large windows, south-oriented. We have to design the right size or the right length for the overhang. And in northern facades, we have something like that. We have something with very small openings and something that it's not as open as the south facade. We have the most, the building I like the most of all these Usonian houses, it's the solar cycle, yes, this one. Okay, so this house, this is the south elevation, and this is the north elevation. Okay, so on the north elevation, the house is even buried. Okay, so it has small openings, and the northern wall, it's not a wall itself. It's just the soil that goes up and covers the house. But then the southern, it's like this, with a long with this overhang and a large window here. Okay, so this is I think this house summarizes Frank Lloyd Wright's concept. It's a very small house. I mean, I don't think it's over 1,500 square feet. So it's quite small. It's not something outstanding. It's just a single family house for a couple without children, probably. But I think this concept summarizes everything. Okay, we will study Frank Lloyd Wright. That if we are designing houses in cold climates, there are things that have to do with thermal insulation, with materials, air leaks. So those are building science issues, but the main issue is the design. So if we design something that is good from the beginning, we have a lot of things solved. And basically, we need to know that we can make the most of the southern sun, and we need to place small windows, small openings on the northern elevation or facade. Okay, let's go back to the lesson. When we have a source of heat here, there will be always three mechanisms to transfer heat. We have conduction, okay, so we need a material, a solid material. So if we place this element, especially if it's metallic here, close to the fire, it will heat up. And if we don't wear gloves, we will burn, okay? This is conduction. We need a solid material to transfer heat from this place to that place. We need convection. So convection means that we don't have to touch the fire itself to feel the heat through the air. So the fire heats up the air around the fire, and this hot air or warm air ends up heating up our hands. And finally, we have radiation. If we didn't have air, okay, and that can happen, we don't need air. So through radiation, we can feel that heat. Okay, so in every single building, we will have three elements. We will have conduction through solids. We will have convection because the heat or the fire or heat source, the boiler, whatever, the fireplace, it heats up the air, and then the air moves and affects us. And then we have solar heat gains through radiation. We don't need air. So that's why we are feeling the solar radiation and the solar heat, because we don't need air to transmit heat through radiation. And this is a wall. Okay, so if we have a wall, do we have a solid body? We do. The wall, the roof, the floor, it's the solid element. If we have a difference of temperature, T1 and T2, imagine that this is, well, if T1 it's higher than T2, then the heat goes this way. Okay, because we have a solid element. The wall is a solid element. So through the conduction, the heat goes from phase A to phase B if T1 it's higher than T2. Then, if this air temperature is different than this body temperature, this body will heat up the air around it, and there will be this convective heat transfer. So through convection, this or part of the heat that we have in this solid body will be transmitted to the air. And finally, we have radiation. If we have a solid body here at a temperature, and we have a different solid body here at a different temperature, the heat will go from the hot to the cold source. If there's a wall, what kind of solid bodies we can have in houses? People. People are solid bodies. And our temperature is different than the temperature of the envelope. So if it's in summer, if we're in summer, the wall temperature probably will be higher than our body's temperature. So the heat will be transmitted through radiation from the hot source to the cold source. In winter, it's the other way around. Our temperature will be higher, our body temperature will be higher than the wall temperature, and then we will transmit our heat to the wall. Okay, so we have three different ways, and we always have three different ways in buildings. We have conduction through the wall. If we have two phases at two different temperatures, we have convection. If we have air and the air temperature is different from the wall temperature, and it's always different. And finally, we have radiation if we have two solid bodies at different temperatures, and we're always going to have two different bodies at two different temperatures, because people are at a temperature, and walls and roofs and floors are at different temperatures. Okay, so we always have three different mechanisms or heat transfer. Then we have this. Last week we learned only conduction, so we calculated the thermal resistance. So the thermal resistance is the thickness of the wall divided by the thermal conductivity. We evaluated that. I taught you how to create this Excel file. You did it. Perfect. But this is only for the solid. But we have to evaluate, or we have to calculate, this component of convection and radiation. And I'm showing you this picture because I'm sure that if you have driven, or if you have at least you have been riding a car or whatever, I'm sure you have seen this, especially when it's too hot. And we have this experience that it's like water, but it's not water. We can see reflections. So this is the car, and we can see reflections here. And we can see how the picture is like, we have this blurry effect. It's like the distorted. And what is this? There's here we have the tar or the asphalt at the temperature, especially if it's too hot and the sun is striking on this black surface, it gets very hot. And then the air temperature is below the asphalt temperature. So we have this kind of effect that we can see that there's something, well, this effect is because the air is moving here, okay? Due to the difference of temperature between the asphalt and the air, we can see that there are small air cells that are moving. Okay, so it's like, well, yeah, so we have something like that. Okay, so there is some air moving here, and that affects our, yeah, that affects the view. It's not completely realistic. We see something that it's not real, and it's not real because we see that this air is moving here. Well, that happens in buildings. It's not as the effect is not as, not like this, but this kind, every time we have a temperature, we have a wall or a floor or a roof temperature, and we have a different air temperature, the air is moving very close to, there's a thin air layer that is moving very close to the wall surface. Well, this is the effect of convection. Okay, so how can we measure that? Again, ASHRAE, the Bible of building science, provides us with these coefficients. Okay, so we have this heat radiation convection coefficient, and this is H. Okay, so H is heat radiation convection coefficient. It's not conduction, because conduction happens only through solids. It happens because the temperature of the wall and the temperature of the air are different. And then we have these small cells moving around it. Okay, so that provides the wall with another thermal resistance that we didn't take into account last week. But this week, we are going to work with these coefficients, with this radiation-convection coefficient. And I stands for interior or indoors or inside or whatever, and E stands for exterior or outdoors. Okay, so we have the interior and the exterior coefficient. Here we have both units. This is international units, and this is imperial units. Okay, and we have these different coefficients for, this is a wall, okay, so if we have a vertical element, the heat flow goes horizontally. That would be a roof. We have a horizontal element. Well, it's a roof if we are in winter, okay, so imagine that below or underneath this roof, we have the hot air, and here we have the cold air, so the heat flow go upwards. And that would be the floor. It's horizontal, and the heat flux is going down, because again, the warm source is here, and the cold source is there, so that would be a floor. Okay, so we have to apply these coefficients. If we have a wall, we have to apply these two values, 1.6 for interior coefficient, 2.93 for the exterior or the outdoor coefficient. If this is a roof, we have 1.96, 2.93. This is always the same. It's always 2.93. But the indoor or interior coefficient changes. This is the wall, this is the roof, and this is the floor. We're going to explain this with an example, okay? But that's the theory. And it's because of this, because we have this air moving very close to the solid surface. Okay, so, well, this is an example. So I'm going to show you that this is the outdoor air. Here we have the indoors. And there will be a wall. So we are going to draw a wall with only one layer. We don't have a multi-layer wall. We are going to, yeah, so we have a wall. Imagine that it can be brick, concrete, whatever. But we have only one layer. So on this layer, this is the limit. And that will, yeah, we have a thickness, okay? So this W, it's the thickness of the wall. And we have a thermal conductivity. It can be either lambda or K. But now we have to add this, well, first we have the temperature. This is 70 Fahrenheit, the indoor temperature. And the outdoor temperature can be 20, the outdoor temperature is 20 Fahrenheit. And now we have those the thermal resistance, we know that it's width divided by the thermal conductivity, the thickness divided by thermal conductivity. And those are the small cells of air moving. Okay, we have, this is the indoor and outdoor heat coefficient, convection heat coefficient. Okay, so we have to apply this thermal resistance to the formula. So it's 1 over HE plus 1 over HA. And this is HE, and the other one is HI. Okay, so at the end, the thermal resistance of this wall, it's the thickness of the solid material divided by the thermal conductivity plus 1 over HI, which is the interior radiation convection coefficient, plus 1 over HE, which is the exterior radiation convection coefficient. Okay, but at the end, we have like 3 layers. We have the solid layer, we know that, but we have 2 thin air layers here and there, outdoors and indoors. Okay, so that creates the first thermal resistance. So this is indoor temperature, this is the outdoor temperature. So before the solid layer, we have this air layer that is creating very small, but we have to take it into account because sometimes can be a big number and we have to take it into account. And this is the thermal resistance. So we have this coefficient and the thermal resistance is 1 divided by this thermal coefficient, or this, yeah, the convection, the radiation coefficient, inside and outside. Okay, so minimum, if we are assessing the thermal resistance of a wall, we need 3 layers: the solid one, the interior air layer, and the exterior air layer. So there are always 3 thermal resistance: 1, 2, and 3. Okay, in this example, as you can see, we have values. We have a brick wall, a 4-inch brick wall, and we have the outdoor or exterior convection coefficient and the interior convection coefficient. We have the thermal conductivity, and this is the thickness. Okay, the thickness is 4 inches. The thermal conductivity is this. We don't have thermal conductivity and thickness of this outdoor air layer or indoor air layer. We do have this thermal resistance. If we go back, you see that this is 1.6 and 2.93. Okay, so this is 1 over 1.6 and the other one is 1 over 2.93. And this thermal resistance of the solid layer is 4 divided by 5. If you divide 4 by 5, it's 0.8. Okay, so at the end, the total thermal resistance is 0.34. 1 divided by 2.93, it's 0.34 plus 0.8 plus 0.62, which is 1 divided by 1.6. So the total thermal resistance would be 1.76. Okay. So this is it. Now we have to complete that table because if you remember, we didn't have these parameters when we designed the table for solid elements. Okay, so what we did last week was this. So we have a thermal conductivity, we have a width. The thermal resistance is the width divided by thermal conductivity. And that's it. We can have different layers. If we only have one layer, that would be 0.8. But now we have to apply these 2 coefficients, the the exterior and the interior convection coefficients, and the thermal resistance of these two layers, the outdoors and the indoor air layer, is 1 over the coefficient. Let's do this with a multi-layer wall. So in a multi-layer wall, there's, let's say that we have a brick wall outdoors, then there's a thermal insulation, and this can be a drywall. Okay, so this is the width 1, width 2, and width 3, and we have 3 different thermal conductivities, 1, 2, and 3. As I told you last week, we need thermal insulation here, so there will be, well, this is, again, we have this indoor layer and outdoor air layer, okay? And now we need, like this, we need a thermal insulation in the middle. And get used to this. So the thermal insulation is the thickest layer. If we have a multi-layer wall, usually thermal insulation is the thickest one. So we have these bricks outdoors and thermal insulation and a drywall. That would be brick, thermal insulation, and drywall. HE and HI. So the thermal resistance, it's 1 over HI. The thermal conductivities, or the thermal resistance of every solid layer, and 1 divided by HI. We tend to think that this is for winter, but that can be in summer. So imagine that we are in summer and the outdoor temperature is 95 Fahrenheit, so it's warm outside, and the indoor temperature can be 74 Fahrenheit. So in this case, the heat will go from the outside to the inside, okay? So the calculations are exactly the same. The thermal resistance is the same for winter and summer. The thermal resistance, because the thermal resistance depends on the material. It doesn't depend on the indoor or outdoor conditions. Okay, so that would be how we calculate a 3-layer wall. A 3 solid layer wall, 1, 2, 3, we have 3 solid layers. We end up having 5 different thermal resistances. So the thermal resistance of the outdoor air layer, the thermal resistance of the indoor air layer, and then thickness divided by thermal conductivity, 1, 2, and 3. 1, 2, and 3. Okay. What's next? So this is next. This is an example of a 3-layer wall. We have brick, we have fiberboard. In this case, fiberboard is just 0.5 inches. It's just for an example because it doesn't make any sense. This is too, it's not enough. So we have to use thermal insulations about 5, 6 inches, 10 inches, 0.5 inches, it's nothing, but for the sake of the example, I think it worked. So for the brick, we have the thermal conductivity, 5, and we have the thickness, 4. The fiberboard is 0.38 thermal conductivity, thickness 0.5 inches. And plywood, the thermal conductivity is 0.8, and we have a 1-inch plywood board. It's too much, but I told you, this is just an example. Here, it's always the same. If we are working with walls, that would be always 0.34, the outdoor thermal resistance of the exterior air layer, and 0.62, it's the indoor thermal resistance of the interior air layer. The total thermal resistance, 0.34 plus 0.8 plus 1.31 plus 1.25 plus 0.62, total 4.32. Okay, so it's quite easy. especially if we are working with an Excel file, because if we are working with an Excel file, we don't make mistakes adding up things or multiplying things. Okay, so we only have to make sure that the formula is correct, and then we only have to enter those elements, the thermal conductivity and the thickness. And if we don't like this thickness, we can always increase that one. And if we are working, this is not an Excel file, by the way, this is a PowerPoint. But if we were working with an Excel file, we can modify this value, and the rest of the things will be modified immediately. Okay, so this is what we're going to do now with the Excel file. So we can open. There you go. This is the Excel file that we designed last time. So you remember that here we have the material, we have the width, the thermal conductivity, thermal resistance, and the U value here. Okay, so let's do it. But now we need to include these coefficients. How can we do that? I can create here another cell, so this can be HI, this can be HE. Okay, let's do that. And if we are working with walls, there you go. Okay, so if we are working with walls, we know that HI is 1.6. So here we can type 1.6, and HE is 2.93. 2.93. Okay. And now we can always, so imagine that we delete these cells here, and here I can type text, and here I can type in. Okay. So here we don't have a width, and we don't have a thermal conductivity. I have a thermal resistance, and the thermal resistance of the exterior air layer is 1 over HI. So I can type here equals 1 over HI. Okay, and here indoors we don't have this. We don't have a width. We don't have a thermal conductivity, and that will be 1 over HI. There you go. Okay, so this is HI, HE. Those values are always the same because it's if we are working with walls, those values will be the same. If we are working with roofs or floors, it would be different. Okay, but for walls, it will be the same. And here we have different layers. What if you need to include one more layer, because we have like 3, 4, 5, 6 layers? You can always click here, right click on this, but on this column, it doesn't work if you right click here, it doesn't work. But if you click here on this, where all the numbers are, right click, you can insert. Okay, so you can insert as many or as much cells as you need. Okay, so I don't know if we have another materials, whatever, another material. So here we can work with different widths. Remember this, so here we don't have any value for this cell, so you have to click here, you have to drag all these elements. So now you have exactly, no, sorry, this is the thermal conductivity. No, sorry, we can work with different thermal conductivities. This is the cell that you have to drag, because here we have a formula, but here we don't have any formula. So you have to drag this here. There you go. Okay, so that will be the width divided by the thermal conductivity. And what about this? If you double click here, yeah, so you see that it has added up all these figures, and this is 12.14. And this is what I told you, that you have to calculate the thermal resistance as the inverse of the total. We don't calculate thermal transmittances here of each layer. We calculate the total one. But we do have these two layers into account that we didn't have last time. Any questions so far?
Nope.
Okay.
No.
So this is it. There is no mystery. It's not difficult. The only thing is that if you are working with your Excel file, make sure that you have this. So we can change the format of this to make it nicer. So we can say that this is HIHE. When we have a title or something that we can edit or we can change, I don't know, I think it's good having this as a different color, and you can change this or that. If we have different walls, we can copy this. I will delete. But if we're working with floors, we can always copy, and paste. And imagine that this is a roof. If this is the roof, we have to change these values. The HE, it's always 2.93, but HI, it's 1.96. So this is 1.96. Okay, this has changed. By the way, I don't like this, so I will apply this format. Okay, because, well, 2 decimals is enough. Okay, so those are roofs. And here we have the, yeah, we always can combine and center. So we can say that this is for wall, combine and center. This is for roofs. Okay, so here we differentiate these coefficients. The rest is the same, but these coefficients, well, only this one, but the convection coefficients are different here. So we have to make sure that we don't make any mistakes. So if we're working with different walls, you can copy all these, and then you can work with different walls. And if we are working with different roofs, you can copy these, and we can work with different. And if we are working with floors, so let's do that. Copy, insert copied cells. That would be a floor. And what is the value of this? Okay, this is a floor, so this is 1.05. So the Excel file, this is 1.05. Okay, any changes? If you don't have enough, or if you don't have all these elements, you can just delete this. And if you want to make it nicer, you can always delete all these cells. But as you can see, this is not affected. And now if you need one more layer, you can always insert layer. And here you can type the material, the thermal conductivity, the width. It doesn't change, but you can always drag this here, and immediately everything is calculated again. Okay, so what are we going to do now? We are going to this is the example, the last example that I showed you. You can check those values to see if you have the same result here. So you have a brick with this thermal conductivity in this width, or a fiber board, or a plywood with the outdoor, sorry, in the indoor. So you can check if the value is the same, the thermal resistance. But now we can modify the problem. I mean, it's the same, but we are going to solve this problem the other way around. Usually, we are limited by this value. So the R total of a wall should be 50. Why? 50 watt, by the way. Don't forget to type units. It's BTU, hour, Fahrenheit square. Okay, so when you have a value, 50 is not enough. We always need units here. And here, the R value, if you want to solve this, or if you want this to be correct, you have to say the R total equals 4.32 BTU hour Fahrenheit square. Good. BTU hour Fahrenheit square. Okay, this is the correct answer. But what if we have this requirement that the R total of this wall should be 50 BTU hour feet square, and we know that we're going to use brick, fiberboard, plywood. We do have this indoor air layer and the outdoor air layer. So what is the thickness of the fiberboard I have to use to meet this requirement? And this is the common issue. We don't select the materials and the thickness, and then we calculate the R value, and that's it, the thermal resistance. No. We have these constraints because we are in cold climates, so we need to increase the thermal resistance. In 50, it's a good limit. And then we need to calculate the thickness of thermal insulation. So what do we do here? So we have to apply always the same formula. R value equals 50, because this is the requirement. So this has to be 0.34 plus 4 divided by 5 plus, we don't know the thickness, so let's say X is the unknown, divided by 0.38 plus the width, it's 1 divided by 0.8 plus 0.62 . So that equals 15. Okay, so this is the problem that we have to solve now. So now we know that 50 minus 0.34 minus 4 divided by 5, it's 0.8. Minus 1.25 is 1 divided by 0.8. 1.25 minus 0.62, that equals x divided by 0.8. So x equals, so I have to solve this. It's 50 minus 0.34 minus 0.8 minus 0.25 minus 0.62. Okay, so this is 46.99. 0.99 divided by 0.38. No, sorry, multiplied. 0.38. This is 17.85 inches. Okay, is it clear? Now we have this constraint, so we need a thermal resistance, which is minimum 50, and we need to provide our client or the constructor or the construction company with the right amount of thermal insulation. So the right amount of thermal insulation would be 17 inches. So we don't have 17.85. So we can say, okay, this is 18 inches. Because we don't have 17.85 inch panels available in the market. It will be 18 inches or 20 or whatever, but at least it has to be 17.85. So we can, very good. So this is around 18 inches. And why 50? Well, you have to internalize this number. Okay, when we're talking about the walls and roofs in zero energy buildings or in high performance energy buildings, the R value 50 is something that we have to internalize. So we don't have to think about it. It has to be 50. And where does it come from? It comes from what we call the passive house standards. Okay, so the passive house standards there are other things too. Let's go to the Passive House Institute of the US. There you go. Okay, so this is a very interesting website. What is Passive House? Passive House, it's something, or it's a standard. I mean, it's like the USO or like ASHRAE. So there are a lot of architects, engineers, and constructors involved in this Passive House Institute in the United States, and they all have the same goal. They all aim to build or design high performance buildings. So the first goal to achieve a high performance building or a zero energy building is to reduce the energy consumption. And one of the ways to reduce the energy consumption is what we have covered before. It's about a huge or the right amount of thermal insulation, and we have to control the air leaks, and we have to control the size of windows and the performance of windows. Well, so this passive house standard is something that comes from Germany, or the first time I heard about this passive house, it was in Germany, but now it's mainstream all over the world. So the first thing you have to do is to reduce the thermal loads. And to reduce the thermal loads, you have to increase the thermal resistance. So if here you click on what is a passive building, there are passive house principles. And the passive house principles are the same thing that we have talked about. Continuous insulation throughout without any thermal breaching. We will talk about thermal breaching later. The building envelope is extremely airtight. Okay, so airtightness is something very important. Windows, double or triple paned. In New Hampshire, in our TDS center, we have triple paned windows because it improves the thermal insulation of windows. Then we need something about ventilation. We have to work with the ventilation. We haven't talked about ventilation yet. And use minimal space conditioning system. Well, that's another design thing. But if we look at the requirements, it's somewhere. But if we are aiming at a passive house building, probably infrequent. Okay, so these are sample R values in different places because we are designing buildings in different places. So look at this. If we are in Duluth, in Minnesota, which is cold, I don't know if it's as cold as New Hampshire or even colder, I don't know. But look at these values. So if we are going to design walls, the air value ranges from 49 to 65. So 50 is good in Burlington, Vermont. Okay, so probably this is closer to our place, to Keene. We don't have to memorize 39 to 51. So just memorize 50, and unless you are building something in Alaska, which you need 89, crazy. But in cold climates, being above 50 is good. Okay, so if you design walls and if your wall R value it's around 50, you don't need that in Florida, and probably you need more in Alaska. But the rest of the places in the United States, it goes well. Okay, so that's where the 50, the R value equals 50 comes from. For ceilings, it's even tougher because look at this. It has to be above probably 70 or 80. Yeah, if it's in Burlington, Vermont, it's from 70 to 90. So we need more thermal insulation in ceilings or roofs. Why? It's very simple. Because heat tends to go up. Okay, so if we have a hot source here, heat tends to go up. So we need more thermal insulation in the roof than in the wall. That makes sense. But look at this. If we are aiming at these passive house buildings, high performance buildings, zero energy buildings, we need 18 inches of thermal insulation. I told you that 6 might be enough. In Florida, probably. But in cold climates, we need 12. Depends on the thermal insulation. This is not a very good thermal insulation, by the way. We will talk about this as well, about different kinds of thermal insulation. But if we are working with this fiberboard, we need 16, 17, 18 inches of thermal insulation. So you can take a tape to measure, or a ruler or whatever, and try to measure 18 inches. and 18 inches is the thickness, the basic thickness of the thermal insulation. Then you can add internal finish or external finish, so you end up having a huge wall. So you have to get used to that. And when we are designing walls have to be thicker. And southern walls maybe can be thinner than northern walls, as we can see in this picture, because this is thinner than that. But especially roofs, in roofs, we either have an attic like this, so this is not, people are not living here, or if we have a roof in which, or we have this space that can be occupied by people, then we need to increase this thermal insulation or the thickness of that roof here. Okay, so there are two ways to do this. First, we decide the thermal conductivity and the width or the thickness of different materials. We calculate the thermal resistance. But look at this thermal resistance is 4.32. Ridiculous. Because a good thermal resistance in cold climates has to be above 50. So knowing that, and if we know what kind of thermal insulation we have, then we can calculate the thickness of the thermal insulation. And by the way, where can we find this kind of elements or these kind of materials? Okay. This is the table that we used last week. So on that table, you see that we have thermal conductivities on that column. But for example, for these elements, we don't have thermal conductivities. We have a thermal resistance directly. Okay, so in this column, imagine that we have a concrete block, a 4-inch concrete block. So a 4-inch concrete block, the thermal resistance is 0.8. So that means that if we are using a 4-inch concrete block, we don't need this thermal conductivity. We need to type here directly 0.8. You understand? So on this table, if we do have the thermal conductivity, we can do this. So we can calculate the thermal resistance dividing the width or the thickness by the thermal conductivity. If we don't have a thermal conductivity on this column, then we have to type directly the thermal resistance. And this is what happened with insulating materials. All these materials here okay, all these materials are thermal insulating materials. We have the fiberboard, which is the worst, by the way. And then we have the extruded polystyrene. Well, here we only, we have the fiberglass, and then we have the extruded polystyrene. Fiberglass and extruded polystyrene. What is this? Fiberglass. Thermal insulation. Yeah, there you go. So this is fiberglass. It's something soft, so it's not rigid. So if you press on this fiberglass, You can shrink the thickness. It can be this color, like grayish or greenish. Usually we have these yellow panels. Okay, this is the fiberglass. Yeah, so this is it. It's always yellowish or greenish. It's not rigid. This is a fire-resistant material, so we can use this to protect our structures against fire. It's cheap, and it's quite good when it comes to this thermal insulation. Okay, so fiberglass, it's a good material, it's a reliable material. We only have one problem with thermal insulation, with the fiberglass thermal insulation. It doesn't bear water, so if it gets wet, it's not a thermal insulation material anymore. So we have to protect this element against water. So that's why we have this aluminum sheet on this face, because the goal is to protect this material, the yellow material, from water. So fiberglass, it's better than this fiberboard. Fiberboard, it's what we call cellulose. Okay, this cellulose, it's like compacted wood. Okay, so those are wood fibers, and they are compacted, and you have a thermal insulation. And now people are crazy about this cellulose insulation. Why? Because it's wood. It's natural material, because those fiberglass and polystyrenes, it takes a lot of energy to manufacture this, and you emit a lot of CO2 manufacturing those kind of elements. But cellulose, it's just, you just grind wood, you stack those wood fibers together, and then you have this kind of panels. So it's very easy to manufacture. It's an ecological material because it comes from wood. Most likely it will come from recycled wood. Okay, so it's a perfect material. The problem is that its thermal insulation capacity is not as much as fiberglass or extruded polystyrene. If you talk to other teachers or other instructors in state college, they will tell you that you have to use always cellulose or wood board or wood fiber or fiber board, the same names here. But in my opinion, well, you can use this. It's perfect. It's a renewable material. It's almost natural because it comes from recycled wood, so it's perfect. But the thermal conductivity, it's too high for a thermal insulating material. That's the only problem. So you need a huge thickness of thermal insulation. What was the thickness here? Yeah, it was 18 inches. Too much. Okay. What about if you use fiberglass? If you use fiberglass, look at this. 1 inch of fiberglass, it's the thermal resistance. Okay, here we have different inches. This is 3/4, this is 1 inch. Okay, so 1 inch, the thermal resistance is 4. Okay, a 1 inch fiberglass board, the thermal resistance is 4. So that means that if we use 6 inches, the thermal resistance is 24. If we use 10 inches, the thermal resistance is 40. So what happens if here I use fiberglass and the thermal resistance is 40. We have 10 inches. So look at this. Imagine that so because that doesn't affect, by using a 10-inch panel of fiberglass, the total thermal resistance is very close to 50. It's 49. And it's only 10 inches. we needed 18 inches of cellulose or fiberboard to have the same thermal resistance. So now we have to make decisions. I don't, there is not, okay, you have to do this. I'm not telling you these kind of things because you have to decide. You will be the architect in the near future, and then you will have to decide what kind of material you want to use. If you use cellulose or fiberboard, it's the carbon footprint of this material is very low. It's made of recycled wood. It doesn't take a lot of energy to manufacture the product. So it's perfect. But then you need to increase the thickness of the thermal insulation. If you want to reduce the thickness of the thermal insulation, then you have to use other thermal insulation materials. Fiberglass is a good option. And another option is the extruded polystyrene. This is what we call foam. It's a polymer, so it's plastic. It's a plastic, and now plastic nowadays, it's well, it comes from oil. So to manufacture this kind of material, you need to extract oil, and then it's a polymer, so it's an artificial material. You don't find this material in nature. You have to manufacture that. You have to produce a lot of CO2. You have to release a lot of CO2. And but when it comes to the thermal properties, this is the best material. And if you are going to expose a thermal insulation to the rain, or you think that it might get wet, this is the right option because this material is not affected by water. Cellulose and fiberglass, they are affected by water. This kind of foam or polystyrene, it's not affected by water. Again, what is the best thermal insulation? When I was a student, everybody told me, well, when was I a student? 3 years ago. Yeah, kind of. Well, 30 years ago, everybody told me, okay, the best thermal insulation material is the extruded polystyrene. And I believe that because my teachers told me, no, you have to use thermal extruded polystyrene. Forget about fiberglass, forget about anything else. Extruded polystyrene. And I did it. But nowadays, things have changed because now we are not looking just at the thermal properties. We are looking at the carbon footprint, how much CO2 we use to manufacture a material. So if we are looking at this, the best material is the cellulose or the wood fiber or the fiber board. And the best and the worst is the extruded polystyrene. Fiberglass is in the middle. And it takes a lot of energy to manufacture fiberglass. But if you want to protect the structure from fire, fiberglass is the best option. So what would I do? I don't know. I would use probably the 3 of them in a single family house. If I want to use, if I'm designing a flat roof, I would use extruded polystyrene. I don't rely on fiberglass or cellulose. And walls, I would use cellulose. And if I want to protect something from fire, for example, a mechanical room, the room where the boiler is, there I would use fiberglass to protect the mechanical room from fire, because we have if we have a boiler with an oil tank or with a gas boiler or whatever, if we need to protect this room from fire, then I would use fiberglass. That's it. But I can't tell you, okay, you have to use this this kind of thermal insulation. You might find people that have an answer to that question. Okay, what is the thermal insulating material that I have to use? This one. I am not that kind of people because it depends. What do you want? Where do you want to? Can you afford to have a thick wall? No, because my wall has to be as thin as possible. Okay, don't use cellulose because you need to increase the thickness. If you want your wall to be as thin as possible, you have to use extruded polystyrene. If it's exposed to water, you have to use extruded polystyrene. If there's a risk of fire, you use fiberglass. If you don't have any constraint about water or humidity or fire protection, or if you don't have any concern about space, go ahead and use cellulose. But what is the best material? It depends. It depends on what? It depends on a lot of things. Okay.